Welcome back to Mrs. Ogram's Maths. We are going to go through a practice differentiation paper now. So this first part is asking us to differentiate e to the x sine x. These are two things multiplied together, so therefore we are going to be using the product rule. So we set out that u is e to the x and v is sine x. I'm using that shorthand notation for differentiating u as u dash. And if we differentiate e to the x, we get e to the x. If you differentiate v, sine x becomes cos x. And if we put them together, then we get the derivative of y is doing that cross multiplication. So that's ex cos x plus ex sine x. And no need to simplify any further on these questions. Part B is we have a diagram of this graph here, and we're asked to find the x-coordinate of point Q, which is a maximum. If we're finding maximum points, we're looking for the derivative to be equal to 0. So we need to differentiate this function that we have here, which is something divided by something else, so we are going to need the quotient rule. So we set out that u is x, v is e to the x, derivative of x is 1, derivative of e to the x is e to the x. And then the derivative of y will be v du by dx, which is e to the x, minus u dv by dx, which is x e to the x, divided by v squared, which is e to the x squared. And then we will set that equal to 0 to look for our maximum point. And with that, we can divide through by e to the x here. So we can divide through there, take out 1 e to the x in each of those. So this becomes a 1 minus x over e to the x. So 1 minus x over e to the x is equal to 0. Rearranging that to solve that, bring the e to the x up and times it by the 0, we get 1 minus x is 0. Therefore, x must be equal to 1 as our answer there. Part C is parametric equations, so the first thing to do is differentiate each of those with respect to t. So if we differentiate x, we have 3 plus ln of t minus 1 becomes a fraction. When we're doing derivatives of ln, whatever's inside goes on the bottom of that fraction on the top. So if we differentiate, dy by dt becomes 2t. Now, if we're doing dy by dx, let me just rewrite that. Dy by dx will be to do dy by dt times by dt by dx. Now, I'm just popping that up at the side, but not carrying on with that just for a minute, because this dx by dt at the moment is not in a form that we can easily flip it over to become dt by dx. I want to put that all into one fraction. So putting it over a common denominator of t minus 1, we would have to multiply the 3 by t minus 1 and then add on that 1. So that becomes 3t minus 2 over t minus 1. Then we can carry on with dy by dx, which will be dy by dt, which is this 2t, multiplied by dt by dx, which is this dx by dt but flipped over. So t minus 1 on the top, 3t minus 2 on the bottom. Okay, so that becomes 2t squared minus 2t all over 3t minus 2. Now I'm just going to copy that down to the next bit of the page so we've got a bit of room to work. So with this, this part here, we wanted to work out, let's just go back to the question, the gradient of the tangent when the curve is equal to 1. So we need to set that gradient equal to 1 and then work out what we've got from there. So if we work that through, this is what we end up getting. So I've just skipped ahead a little bit solving that quadratic. We get to t is a half or t is equal to 2. Now look back at the question and we're told that t must be bigger than 1. So we can't have a half. That's an invalid solution. So therefore, this is the solution that we're looking for. Now, we're not quite finished because the question asks for the x-coordinate. So we take this here and we need to put in that t is equal to 2, and then we can work out x. So when t equals 2, this gives us that x equals 6. You can just plug it into your calculator by putting 2 in for t in this part of x. Alright, part D, we're talking about a spherical snowball with a radius of 5 centimeters melting at a rate of 0.5 centimeters cubed per second. So we're first of all going to write down that rate. This is a rates of change question. So the volume over time is changing by going down by 0.5 centimeters cubed per second. That's that bit here that we're told about the rate. We are being asked to find the rate that the radius is decreasing at. So we want dr by dt. If we know dv by dt, we need to work out what pieces we'll need. So we'll need an r on the top, and we will need a v on the bottom to cancel that out, which would end up giving us dr by dt. So that's what we're aiming for. So we need a formula that links v and r so that we can do this dr by dv part. So the volume of a sphere is 4/3 pi r cubed, which means that if we differentiate that, we can get dv by dr, which is 4 pi r squared. And if we move that across to working out dr by dt, well, dv by dt we were given, it was minus 0.5, and we're multiplying that by dr by dv, which is 1 over 4 pi r squared, because it's the flip of dv by dr. So we're just left with minus 0.5 over 4 pi r squared. Now we're being asked to work out what that rate is when the snowball is at half. To know what r will be, so we can, our initial volume, which I'm going to call v0, so our starting out point, was that the radius is 5. So if we put 5 into the formula for working out the volume, we will end up with 500 pi by 3. So half the volume will be equal to 250 pi by 3. Now for that to be true, this will give us an R value of 3.97 centimeters. Okay, so that's just using our volume formula there. So if the volume got half, I'm equal to 250 pi by 3. Okay, now we have a value for R. So at half volume, the radius is 3.97. So dr by dt is equal to minus 0.5 over 4 pi times 3.97 squared, which equals minus 0.0025, and we want to know what units that is. So we are measuring something that's in centimeters, the radius that is, and that's according to time, which is being measured in seconds. So centimeters per second, or if you prefer, you can write it as centimeters s to the minus 1. All right, the final part of question 1 is our excellence part. We want to find the value of a which satisfies this equation. So first of all, we need to work out what the value of d2y dx squared would be, which means we have to differentiate y twice. So dy by dx, we have a product rule here. So we need to do, in fact, I'm going to write out the whole thing just to be sure. So u is x, v is sine ax. U dash is 1, v dash is a cos ax, because a is just a number. So if there had been a 2, we would just stick the 2 out in the front. It's the same with the a. So now y dash becomes u times dv by dx, so this one here. So ax cos of ax plus 1 times sine x. So sine ax, that is, sorry, not sine x. So there's our first derivative. Now the second derivative, so d2y dx squared, will be to differentiate y again. Now once again we have a product rule in this first part. I am going to do this without writing out the whole thing, but I'll talk it through. So this bit, ax is our first part, so if we do ax times the derivative of cos ax, so ax times by the derivative of cos ax is minus a sine ax plus cos ax times the derivative of ax, which would just be a. Then the derivative of sine ax is a cos ax. And if we tidy that up, we get 2a cos of ax minus a squared x sine of ax. Okay, so now we want to show that this thing here equals this thing here. So we take that function that we just did and add on 9y and hopefully be able to show that it equals this bit here. So d2y dx squared plus 9y will be equal to this d2y dx squared that we just worked out, and then add on 9 lots of y. Well, 9 times y is 9x sine ax, because y was back up here in the question. We just do 9 times that. Okay, so carrying on with that, if we've been given the equation to solve where this thing equals this thing, so this thing is equal to this thing, so this is equal to what we just had up here on that line down there, and now we need to work through with that. So we can cancel out these two on this side, they're the same. A squared plus 9x sine ax will be equal to 0. We can take out a factor of sine ax from both of those, and we're left with a squared x minus 9x is equal to 0, and a squared x minus 9x from there must be equal to 0. We're not doing that sine ax equals, because we've told that a was a positive integer up here, so if sine ax was equal to 0, a would have to be 0. So we know that the factor of x, and we get a squared minus 9 is equal to 0, so a squared equals 9, a equals plus or minus 3. You must show that steps that a could be plus or minus 3, but then pick the right one. So we're told that a is a positive integer, so therefore a is equal to 3. And on we go with question 2. Now we're differentiating x minus ln x squared minus 1. We've got a polynomial here in 2 different pieces. You just differentiate each of those pieces separately. So y dash becomes the derivative of x is just 1. And if we are differentiating ln, it becomes a fraction where we have the original on the bottom and the derivative of what was inside goes on the top. And that's all for part 1, or rather part A, I should say. Now, velocity and acceleration are linked in that if you differentiate velocity, you get acceleration. So with v, we are going to differentiate v. So v is the square root of 6 minus x squared, which is 6 minus x squared to the power of a half. So if we differentiate that, that is the chain rule. So a half 6 minus x squared to the minus a half multiplied by the derivative of the inside, which is minus 2x. So that is equal to minus x over the square root of 6 minus x squared. If we're putting it into similar terms or things we can easily work with, you don't have to rearrange it to this. You could actually just leave it in this first form here. So we're asked to do that when x is equal to 2. So when x equals 2, the derivative of v, or the acceleration, is equal to minus 2 over the square root of 2, which is minus 1.414 meters per second squared. Now for part C here, I just need to make a little smaller to fit it all on the screen. I love these questions. I think they're really easy merits. It doesn't take too much to try and understand what's going on the graph. All right, so first of all, what's the value of f of minus 4? So minus 4 is just here. And we want to know what would we read off from the graph. Well, we've got 2 values. We could either go up here to a 7 or down here to a minus 5, but an empty circle means it's not included there, and a full circle means it is included there. So the value at minus 4 is this one where the full circle is. So we are going for f of minus 4 will be equal to minus 5. for what value of x does the function different numbers? So if we were coming from the left at this point and from the right at this point, we would be heading to different places. So at -4, we do not have a limit. Now, if we look at other places on the graph where you might think about it, you might consider this one, but that does actually have a limit there. From the right and the left, they are heading towards this same point. Even though it's an empty circle and we don't have a value there, it doesn't mean that there isn't a limit. So you can have a limit even though you don't have a value of the function. It's heading towards the same number. That's what the important thing is. Same with the same at the point of x equals 5. They're both heading towards 5, so that does have a limit. But this one here, if we're looking at x equals 7, from the left we're heading towards this number here, but from the right, if we work backwards, we would be heading towards that number. So they don't have a limit at x equals 7. Okay, find all of the values of x that meet the following conditions. So f dash of x is less than 0. This means the gradient is negative. So negative gradient means we are coming down, which is this first bit on the graph. So it's down until we hit -7. At -7, it's a turning point, so it would be equal to 0 there. So we want x is less than -7 is our first thing. Now, another point of the graph where we have our downward sloping gradient is here, so that's between 5 and 7. So x can be between 5 and 7 is written like this. Okay, next bit. We want the gradient is equal to 0, so we're looking for turning points. And the second derivative is greater than 0. Now, the second derivative means that it's not just that we have the gradient is equal to 0. Second derivative is that we have a minimum point. So where's the minimum point on our graph? It's right here, when x is equal to -7. Okay, and f of x is continuous but not differentiable, so we don't have a gap in the graph. But something weird happens there, and for these ones you're looking for where there are sharp corners that you can't do anything about. Okay, so this here is not continuous, so let's not even consider that bit. This line here carries on, that's continuous, no problems. Here we've got not continuous, so don't count that. But here we have it being continuous, there's no break in the graph. But we can't differentiate at that point because we wouldn't know whether to differentiate it according to the line on the left or the line on the right because it's got that sharp turn in it. So we can't differentiate when x equals 5. We've got another break in the graph here, but then, so that's not continuous, we're not going to include that, and nothing else after that point. Okay, carrying on to part D. We have another product rule, so we've got u is x squared minus 3, v is e to the minus x. So we carry that on like so, put them together to find the derivative. Oh, I missed a negative there. X squared minus 3 plus e to the minus x. 2x, so we're just using the product rule, using that, cross those over, times them together, add them up. Okay, now we need to find the values when that is equal to 0. So we can take out a factor of e to the minus x, and we will get minus x squared plus 3 from the first one, because look, there's this, oops, the minus at the front there, so we need to make sure that minus goes back into that bracket that we've taken out here, because we're only taking a positive e to the minus x out. And then plus 2x from this bracket here is equal to 0. Now we know e to the minus x cannot be 0, so minus x squared plus 3 plus 2x must be equal to 0, and I'm just going to reverse the signs of that so that it's easier to deal with, and actually I'm going to put it in a different order as well because I like to see my quadratics like that. So now we can factorize it into x plus 1, x minus 3 equals 0, so x is equal to minus 1 or 3. And here we go with the excellence question. Okay, so we've got this pepper seller that we're doing some stuff with the volume and surface area. We want to make the minimum surface area for the pepper cellar. So we need to have an expression of surface area and try differentiate it and set it equal to 0 to find a minimum. So let's start by figuring out what we can do with the surface area. So the circle on the bottom will be pi r squared. The wraparound part of the cylinder is 2 pi r times the height, if we call this the height here. Oops, there we go, let me just fix that up. Alright, and then the hemisphere on the top, it's half of a sphere, so that's 2 pi r squared. You have got the formulae on your sheet for spheres, so surface area, volume, all that sort of stuff. Okay, so the volume we know is equal to 140. And the formula for the volume will be the volume of the cylinder plus half the volume of the sphere, and we set that equal to 140. Now we can rearrange that to get h in terms of r, because we want to get rid of this h. We can't differentiate this function for the surface area while it still has an h in it. We need it all in r's. So first of all, rearrange it so we've just got the h term on the left-hand side, and then we can take away that bit of pi r squared by dividing through by pi r squared on these terms on the right. And just do make sure you divide through by pi r squared on both of those terms. Note that I've taken away the pi and, oh, I copied that down wrong. That was a cubed. Pi r cubed became 2r, the r squared came out of it, so we're just left with 1r. Okay, now we can rewrite the surface area as pi r squared plus 2 pi r multiplied by h that we just worked out, plus 2 pi r squared. Which simplifies to this. We've collected up the pi r squared terms and multiplied out this bracket. Now we can differentiate that expression. We get 6 pi r minus 2at r to the minus 2 minus 8 pi r over 3, and we want to set that equal to 0 so we can minimize it. So I'm just going to pause the video while I put the working out in there. It's quite long, so once it pops up you might want to just pause and read through it. So rearranging that, we can then get down to the point where we've got some numbers we can put in for r. So then you would cube root that and you get r equals 2.99. Now we're doing this for surface area, so we've got the radius is 2.99 centimeters. So when r is 2.99, the surface area is equal to 3 pi 2.99 squared plus 280 over 2.99. This is the formula that we came up with way up at the beginning, just putting the radius into that formula. And that gives us an answer of 140.46 centimeters squared. Right, now we carry on with question 3, and we have ourselves a quotient rule to start us off with part A. So we have that u is tan x and v is x squared plus 1. So the derivative of tan x is sec squared x, and this is on your formula sheet. Derivative of x squared plus 1 is 2x. Put that together to get the derivative of y, and we get x squared plus 1 sec squared x minus 2x tan x, and we're just putting it together as the quotient rule, which is also on your formula sheet, and we don't need to do any simplifying. Okay, part B is parametric equations, and we have that dx by dt first would be cos theta, dy by dt would be minus root 3 sine theta, just from differentiating these two expressions that we have here. And we want to find the gradient being at when theta is pi by 4. So the gradient dy by dx is dy by dt times dt by dx. So dy by dt was minus root 3 sine theta, and dt by dx is 1 over cos theta. So it's the flip of this thing. When theta is equal to pi by 4, you can pop that into your values here. We get that dy by dx will be equal to minus root 3. Possibly the decimal answer as well. In this one, you don't really get marked down if you don't do the decimal answer. We haven't been found for the exact value, so it'd be nicer to do it as the square root of 3 and recognize those exact values where you can, but you're not going to get marked down if you don't. Part C is a rates of change question. And we've got the area of an equilateral triangle is increasing at the rate of 4 centimeters cubed per second. So the rate of change of the area is 4. We want to find the rate of increase of the sides. So we want to work out how much x is increasing according to time. So that's going to be the same as doing dA by dt multiplied by, so the thing we've started with, we're going to introduce the x and try to remove the a. So those dA's would cancel, we'd be left with the dx by dt that we're looking for. So first of all, we need to have a formula that links those two variables, the a and the x. How do we get the area when we know what x is? So I'm going to go with half the base times height. So area is half times x times the height, where this right here is going to be our height. Now, how can we work out the height? Well, this is 60 degrees in the corner because it's an equilateral triangle. So the height there, you're just using a basic trigonometry, will be x sine 60. So the opposite is equal to sine of the angle multiplied by the hypotenuse, which would also be x. So going back to our area, we've got half times x sine 60 for our area formula, which of course is half x squared sine 60. Now, if we are differentiating this, then we can start by replacing the sine 60 with its value. That's one of our special triangles. So sine 60 is actually the same as root 3 over 2. So we end up with root 3 over 4x squared. So dA by dt, if we differentiate that now, we'll bring the 2 down, it become 2 over 4, so that becomes a half. So root 3 over 2 times by x. So now we go back to what we were looking for, which was dx by dt will be equal to dA by dt, which is 4, multiplied by dx by dA, which is this thing flipped over. So it will be 2 over root 3 times x. And x, we're doing this when x is 4 root 3. So if we replace x with 4 root 3, then root 3 times root 3 is 3. 4 times 3 is 12. We get 2 over 12, which is 1/6. So we end up with 4 over 6, which cancels down to 2/3 centimeters per second. Part D, we want the equation of the normal. It's important that we note it's the normal, not the tangent. So we need to find the gradient first, and then we'll do the negative reciprocal of it. So we want the gradient of this one here. We're going to have to differentiate f of x. So we need to use the chain rule here. I'm going to write it out a little bit because it is actually a chain rule within a chain rule. So we have u is sine squared x, which is actually equal to sine x squared. Sometimes it's easier to think about it like that. So the derivative of sine x squared, this is chain rule, so 2, reduce the power to 1, leave the inside unchanged, multiply it by the derivative of the inside, which is cos x. Now, the derivative of f of x will be 1 over u. So if we then put that back together, then we get that f dash of x is equal to this thing times by this thing. So we've got the 2 sine x cos x over u, which was sine squared x. So that one of those sine x's will cancel out, so we get 2 cos x over sine x. Now when x is equal to pi by 6, which is what we're given in the question up here, then we get the gradient will be equal to f dash of x, which is equal to 3.464. And actually, I'm not going to do it in decimals because we can do this as exact values. Cos over sine is 1 over tan, which means it's cots. So this is 2 cot of 60 degrees, not 60 degrees, of 30 degrees. So we can do that as an exact value instead. So cot 30 is equal to root 3. So if we were to do cot 30 times by 2, we would get 2 root 3. We're also going to need the y value at that point on the line, so we can do our equation of the line. So we pop pi by 6 in for x here. So sine of pi by 6 is going to be a half. So sine pi by 6 is a half. If we do a half squared, we get a quarter. So f of x will be equal to ln of a quarter. Okay, now do y minus y1 equals mx minus x1. So y minus ln of a quarter is equal to, m is the gradient, which has got to be the negative reciprocal of this, so minus 1 over 2 root 3 x minus x1, which is our pi by 6. So we end up with y is equal to minus 1 over 2 root 3x minus, actually it's going to end up being a plus, isn't it? So this minus times the plus pi by 6 here is going to give us pi by 12 root 3, and then add on the ln of a quarter. And finally, part E, our last bit of excellence on this paper, is a curve is defined by this expression here where we have p. P is a positive constant, so it's just a number, we just don't know what it is right now. So x has got to be positive. The y-coordinate of the point of inflection is what we're looking for on this curve. Oh, actually, there was a typo in this paper, which I haven't fixed just here. That should have been a plus. So this here is x squared plus 1. And we'll carry on with that. So we have y is equal to p x squared plus 1 to the minus 1. That makes it a bit more easier to differentiate. So y dash will be minus 2px x squared plus 1 minus 2. We're using the chain rule there. And then we need to do the second derivative because we're looking for a point of inflection. Now, point of inflection happens when the second derivative is equal to 0. So we need to do the second derivative, but we have a product rule here, so we're going to do it in pieces. So we have the first piece and the second piece, like so. And differentiate each of those, we get minus 2p, and we've got another chain rule here, so we have minus 2 x squared plus 1 to minus 3 multiplied by the derivative of the inside, like so. So then the derivative of y will be this bit times this bit, so we get 8p, oh, hang on, let me just tell you that, but 8p x squared plus 1 to minus 2 minus 2p x squared plus 1 to the minus 2. Sorry, a little transcription error there. This one here should be minus 3 because it was from this v dash part. I wrote it down wrong. Okay, so if we tidy that up a little, we'll put it as a fraction. So we get 8p x squared is over x squared plus 1 cubed minus 2p over x squared plus 1 squared. And we want to set this equal to 0 so we can look for the point of inflection. Okay, so what we can do with that now is put it all over a common denominator. If we put it all over x squared plus 1 cubed, then we keep our original 8p x squared here. but this one, we're adding in another x squared plus 1 on the bottom, so we need to put 1 on the top as well. So we get that extra x squared plus 1. So that's equal to 0. Now, of course, if we bring that up and cross multiply, we will just be left with the top line is equal to 0, like so. Which means that we can factor out a 2p. Like this. So we get 3x squared minus 1 is 0. X squared equals minus a third. So x equals plus or minus 1. Oops, not minus a third. What am I doing there? That's a positive third. Plus or minus 1 over root 3. Now, it'd be very tempting to stop there and think you've got to the solution, but we haven't yet. We've been asked to work out the value of p here, and we're told that x is positive. Right, so let's go back here. We've got two possibles for x, so x must be the positive one. X is 1 over root 3. So that gives us that if we look back up at our equation here, we can pop it into this. Also using this bit here where we were told that y is equal to a quarter. So a quarter is equal to this expression here when x is 1 over root 3. So we end up with a quarter is equal to p over 1/3 plus 1, because that's 1 over root 3 squared from our formula up at the top. So if we rearrange that, we get that p is equal to 1/3. There you have it, all done.